Hi there, thanks for joining in today. Today I want to talk about using a VFD to control a single phase permanent split capacitor motor. So a lot of AC induction motors, if you take them apart, you will find a running capacitor. Now, this only works with the motors that do not have a clutch inside. So if your motor starts up and you hear a click, that has a start um, and possibly a running capacitor in which the start capacitor is brought out. And you cannot do this type of modification to run those type of motors with VFD. However, if it has a single capacitor and there is no click, there is no centrifugal clutch, this is called a permanent split capacitor motor. So that means that this capacitor is on a separate set of windings and it's always engaged, and it's what sets the phase relationship between the two windings to give you the torque and the RPM. The RPM is actually set by the coils themselves, but the capacitor in conjunction with the secondary coil is what sets the phase relationship to maintain that torque. So in this case, what we end up doing is we take out the capacitor and we substitute in and wire in a VFD. Now I'm going to show you this in a diagram. So here is our permanent split capacitor motor. So it's a 120 volt motor, and we have line and neutral. So it comes across, it goes through a switch, and we have a primary winding and a secondary winding in which the running capacitor is in series with the secondary winding. So what this does is, let's just see if we can't get the focus always in one spot as it keeps on coming in and out of focus. There we go. So this capacitor, in conjunction with this winding, is what produces the rotating magnetic field of the stator to allow the motor to run. In a three-phase motor, we have three sets of coils in which the coils are joined together at one end. This is called a delta configuration, and the other end of each of the coils runs off to the three phases. So you have one phase, second phase wire, and the third phase wire. I've drawn these two. You can see a very similarity that we actually have two of the three phases with a permanent split capacitor motor. If we turn around and look at what we're doing with this situation, we're going to remove the capacitor and connect this up to the VFD in the same way, where the primary one is going to be connected up to the W terminal, the secondary is going to be connected up to the U terminal, and the neutral, which was where it was tied off and comes down, would normally go to the neutral, is going to go to the V terminal. And it's basically the same thing, but there's no inductor here. Now what's going to happen is normally these two coils are 180 degrees, or whatever the capacitor sets it up. It's not actually 180 degrees because it's whatever the phase relationship is between the capacitor causing a lead or lag situation with the secondary coil to establish that running relationship. When we hook it up to a VFD, the relationship between the terminals will now always be 120 degrees, so it might not be optimized, but it still works. So in this situation, as we look at this, we have the primary lead here running through and just connecting to my plug right now. So it's connected to the hot wire. The neutral comes to my V terminal, to my U terminal. Let me just take a look. No, my V terminal, pardon me. And then the U terminal, so we'll go back and correct that drawing. So this is V, this is U. So right hand, middle, left hand. No, I did have that right. This is U. This is V. We want the neutral to be the one primary for that. So, and then what I did is I measured which of the two capacitor leads is going to have a certain amount of ohms. It's going to have 8 ohms when compared to neutral. If I do the other lead, it's 0 ohms to the hot lead. So one of these is 0 ohms to the line. That's not the one we want. We want to just remove that and cover it over. The one that we go from from one of the leads to the neutral, and we get some form of resistance. In this case, it's 8 ohms. That's the one I connect to my VFD. So I come back over, and that's now to my U channel. And we'll see that this can actually operate. So in the VFD, I've got it actually up and running here. Let me just pause and connect this in so we can actually be more stable. So in this mode, I've got quite a few different display modes here. So what I'm going to do is, this motor is a 1750 RPM motor that I'm going to be referencing here. And because it's 1750, I have to do some modifications, but this will still work with a 3000 or 3600 RPM motor that is in some of the your normal standard grinders, or even some of those Harbor Freight 1x30 type motors that are 3600 RPM. So in this case, my number is going to be slightly different because I'm 1750. Now, what happens is that if I look at this is my running frequency. It's flashing because it's stopped right now. This is my requested frequency. So if I have my frequency set to 60 hertz, I will be running this at 1750 RPM. So if I turn around and cycle through this, this will be roughly 1800. I've got just a slight scaling issue here. So it's going to tell me 1850. Well, that's close enough to 1750. As I cycle through this, there's a couple things that I can see. This is my running frequency. So right now it's flashing because it's stopped. This is my requested frequency. This is my amperage. So I'm able to tell the unit, and I see here that I'm running 120 volts, 60 hertz, and 3 amps for this motor. And I cycle one more time. That's the voltage, and that's my set RPM. This is my temperature inside the VFD of 24 degrees Celsius. So if I turn around and hit start, we can see the motor's turning this way. I'm running at 60 hertz now. My command is 60 hertz. I'm running 2.6 amps, which is under the 3 amps. So now let's go ahead and slow this down. Let's say we want 1000 RPM. There's roughly 1000 RPM. Running 34 hertz. Command is 34 hertz. And we're drawing in the leads 1.8 amps. So as we can see with the VFD, when we lower the frequency, it doesn't necessarily always increase the current, because the VFD is able to manage the phase relationship to the windings. Now if I grab a little piece of metal here, we can see that I've still got good torque even at that low speed. Let's even drop it down to, say, 500. See if we can get down to there. So there's 500, and now probably I'm going to stall it out. It's still working away. Let's take a look, see what our amperage is doing as it does that. So we've got 1.3 amps. So as I stall it out, it can increase the amperage, but it still doesn't get to my 3 amps. Because that's what I've told the VFD is my motor amperage, is 3 amps. The voltage, let's just cycle through one more time. Right now I'm running 32 volts on the coils at 16 hertz. I go back up to 60 hertz. I'm up to 1780 RPM. Now, if I can increase, I can actually make it go higher because I'm changing the frequency. Actually, I actually run this unit at a speed greater than 1750 RPM because I'm now running at a frequency of 81 hertz. The other thing too about using a VFD is that I've actually got active braking. So if we watch the light, I can hit stop. The frequency is dropping. I've still got power applied to the coils, but it's like doing active braking. When the power shuts off is when the light shuts off. So it actually slows the motor down much faster than if I turn the switch off by the unit itself. Now, one other thing that it can do with the VFD is, I'll turn around and let's say we've got a nice slow RPM, I can change the rotation. So if I hold the forward and reverse button down, here's where it stopped, and now it's going to go the other direction. I have to hit the stop, and I can reverse the direction because it's operating in basically 3-phase. We can see we're still at 13. Let's go back up to the 1700, 1800, so 60 hertz. If I hit stop again, so the VFD allows me quite a few benefits by turning around and having forward and reverse. And active braking, because the voltage is still applied as long as the light is on, because the light is in parallel to the coils. Now you might ask, how does a person set this up? The key thing about this is that you have to have the right VFD in order to use this type of a system. So in this, we look here, this VFD, the model number is H100-2.2 C2-1B. So it's a 2.2 kilowatt, and it is between the C2 and the 1B. It's a single phase input, 110 volts, and it's a 3-phase output from 0 to 110 volts, and it'll output up to 12.5 amps anywhere from 0 to 1000 hertz. So the key element is, if you want to do something like this of driving a permanent split capacitor motor that is normally a single phase motor running at 110 volts, you need to find a VFD that is single phase input and at 110 volts and up to 3-phase output at 110 volts. Not 220, not 220 input. It has to be 110 volts in, 110 volts out. And that's where this model number is. There's various models of this type of a VFD.